That's my guess. Okay, that's there. All right, then, oh, here's one more. The computer just randomly turns off? That's a horrible feature. Okay, that makes things terribly inconvenient. All right, well, we'll see what we can do. This is why, hello YouTube, I record these now so that you're not reliant on the technology to operate live in order to actually get anything done. It is recorded and saved and available for later, if ever necessary. Okay, always have a backup. All right. Anyways, good morning, everybody. Welcome to Busy Wednesday. We've got a whole bunch of stuff to dive in for today with our section on 4.2, the unit circle. So I'm not going to waste any more time. Oh, and Alex is here too. Excellent. Okay, there's a lot of specific pieces that the book section looked at, and I love the book for it, breaking things down into individual tasks and skills. But I'm going to try to group things together and give you a little bit broader picture here on the unit circle. Specifically, how you can build the unit circle from memory in 3 easy steps. Okay? So this is something that I do not recommend trying to just memorize the whole thing in its entirety. There's a lot of numbers there. So instead, we're going to break it down because there's a lot of symmetry and a lot of easily identifiable relationships that we can more easily remember and then build up from there. Okay? So my recommendation is to commit only these 3 items to memory and then use that to create from scratch your unit circle as necessary. Okay? Only as much as you need it. So say on a full test, you might quickly draw out the whole thing so that you have the whole thing for reference. But on an individual question, maybe you're only using half of it or this quadrant of it, or you only need this piece of it, and so you can just work from these basic pieces and build up to enough to get your answer. Right? So these pieces are 30 is 6 and 6 is 3. Item number 2, 45 is 4 and 4 is 2. And then step 3, add more slices. Okay, I'm actually going to start with the third one last, just big picture here. The unit circle is super symmetrical. Right? Everything in the top half mirrors everything in the bottom half. Of course, you just have a negative sign on all the y values. Everything on this side mirrors things on that side. Okay? So it matches quite nicely. So that really you only need to remember a quarter of the circle, and you can quickly mirror it and build up the rest of it from there, just counting up, adding up your angles. But even that is too much because the unit circle is also symmetric across the diagonals, and thus you really only need to remember 1/8 of the circle. Let me put a different colored line here. Okay, there is about there, right? That's all you need. Build from that, okay? So if you remember the first item, 30 is 6 and 6 is 3. This first angle in here is 30 degrees, also known as pi over 6 radians. Okay? All of your radian measures will be some fraction of pi. Okay? Because it's 1 pi to go halfway around the circle, 2 pi's to go all the way around. So this top half is always going to be less than 1 whole pi. Okay? The bottom half will be more than 1, but less than 2 whole pi's. So it's always going to be some fraction with pi. So all you need to remember, really, the only thing that's unique per item is, which fraction is it again? And if you remember, all of the angles are based on some multiple of either 30 degrees or 45 degrees. Right? This guy in here is 45 degrees, except 45 is 4. Right? Recognize if half a circle is pi, then the quarter circle is pi over 2, and then the 1/8 circle is pi over 4. So 45 is pi over 4. If you can remember these two things, you can build out from there. Right? Let's go with orange here. And all we have to do is, that's not quite right. So let's go a little bit closer to the 45. There we go. Double our 30. Double that makes 60. If you double pi over 6, now we have pi over 3. Okay? These will always be alternating, mismatched. 30 gives you over 6. 60 gives you over 3. Okay? Swapping the 6's and the 3's. Swap the 6's and the 3's. The 45, the one that's perfectly down the middle, the symmetrical one, has the most matches. So we got 4 on 45, pi over 4. 4 and 4. Right? Which is why I said 30 is 6 and 45 is 4. But now we also need the actual location, right? Where is this point? What are its coordinates x, comma, y? Right? Because that will give us the actual sine and cosine value. Okay? Remember, sine always gives you the y value. Sine is how tall your movie screen is. Cosine gives you the x value, the horizontal, how far away the movie screen is from you sitting at the center of your dome. And so now we need to remember that. Well, there's only a couple numbers to be involved here. There's the real simple one, half. There's the funky one, square root 3 over 2. And there's the slightly symmetrical funky one, square root 2 over 2. Right? These are the only 3 numbers you need, and we just got to make sure we put them in the right place. And so if 30 is 6 and 6 is 3, this guy gets the one with the 3. So we know the root 3 over 2 has to go in here somewhere. And I would say you need to have memorized sine of 30 degrees is a half. That doesn't look like an n. If you remember that one fact, sine of 30 is 1/2. It will save you so much time because that is the #1 most commonly used, especially on standardized tests. They love their 30-degree angles. Next best would be the 60-degree angle, which mirrors it. Okay? So if you know sine is 30 degrees is a half, you know sine is always the y value, so we know we have to put this guy is the 1/2, this guy gets the root 3 over 2. Okay? So 30 is 6, 6 is 3. 3 comes next. So if you do those in that order, you can build up your next quadrant. And we'll get to how to build out to the others in a moment. We got to start with our basis here. The next one is easy. The 45-degree angle. Right? 45 is 4 and 4 is 2. We get our guy with the 2, all of the 2's. 2's, 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 symmetry, symmetry, symmetry. This is root 2 over 2, comma, root 2 over 2. They match perfectly. Oh, that makes it so simple. And then the last guy, the 60-degree angle, building up from there is, hey, wait, I can just create this because I already know this one. I just reverse it. Flip it backwards, okay? So we swap the x and y. 1/2 comes first, then root 3 over 2. Right, so now we've filled out the full quarter. From just this 1/8 section, we can fill out the whole quarter. Okay. I'm going to gloss over these guys. I hope you recognize the ones on the axis. Okay. And -1, 0, and 0, -1. Right, that fills that in. We know that that must be, let me go back to green here. So the angle-wise, of course, this is 90 degrees, or pi over 2. We're halfway to our half circle. Those are the easy ones. Now it does get tricky, right? Now we've got to add in the rest of them. I fully acknowledge that this is where things start to get tough. But they're not too bad, okay? Because it's the same numbers repeated over and over again, okay? I don't need you to immediately look at this and recognize, oh yeah, that's 150 degrees, boom. Like, you don't need that. You need to know symmetrically, wait, this is the lowest one in the quadrant closest to the x-axis. Oh, that matches the 30 degrees. So this is 30 degrees. Well, you already remember from geometry, I would hope, that the half circle is 180. So all the way around is 180. Subtract 30 in your head. 180 minus 30 brings me back down to 150. Oh, so this is the 150 degree mark. Same with the radians. You can say, oh, this is the pi over 6 radians. You can subtract 1 pi minus 1/6 of a pi leaves me with 5/6 of a pi, right? Coordinates-wise, I'm going to match all of these same numbers. The only thing I'm changing is where the signs go. The x's get negative over here, negative root 3 over 2 comma 1/2. All right, in fact, we could do the rest of those. Negative root 2 over 2, root 2 over 2. Right? Negative 1/2 comma root 3 over 2. And then now you have half a circle. Now you can mirror it below. Just take all of these, copy them straight down, except put a negative sign on all of the y values down here. Okay? Not too shabby, right? So again, you're building up your unit circle, not trying to force yourself to remember every single position everywhere it is. I don't do that. I never bother doing that. Okay? With enough use and practice, you might pick up on some of them and see frequently enough, but honestly, they don't come up. Any one of these in these other 3 quadrants are not common enough to bother remembering exactly right off the bat. Okay, they do not need to come automatically. These should eventually become automatic. Okay, and yes, you should have. Not the super bright yellow. Your 180, your 270, your 360. You got to recognize those numbers. And of course, full pi, 3 pi over 2. And 2 pi. But the ones on the axis should be automatic, and then make this first eighth of the circle automatic. And you're pretty much good from there. Okay? So any questions on remembering and building the unit circle? No? All right, then let me go through. I might have too many examples and not enough time. So let me try to go quickly. So stop me if you have questions. Using the unit circle to solve all your problems, right? Once you have this unit circle, either already in your notes for reference in the homework, or you can recreate it from scratch on the test to then reference for the rest of the test, a lot of these questions become super simple. Right? Find the value of cosine of negative 11 pi over 6. You're like, oh my gosh, 11, that's a lot of pi's. Holy cow, that's not the first quadrant. I don't even have that one on my circle yet. What am I going to do? Don't panic. Okay, negative 11 pi over 6. Oh, that means we go this way. We're counting in pi's over sixths. Okay, that means we hit every axis, and we hit, in this case, every green and orange. Right, we're going 30, 60, 90. We're going to skip all the 45 marks. So we know there should be, right, 1, 2, 3 dots in between each of these. Right, 1 right in the middle, 2 right next to it. These represent every pi over 6, because we remember our first segment, 30 is pi over 6. That's our smallest increment we will have to bother with. We just go backwards and count up 11 of them. 1, nope, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Really? Really? We're right back here? Yeah. How'd that happen? Well, 11 pi over 6 is almost, right? We're 1/6 short of, this was 12 pi over 6. You'd immediately recognize, oh, that's 2 pi. I'm 1 shy of go all the way around the circle. Yeah. Okay. So then the cosine is, we can say that this is exactly equal to the cosine of pi over 6. So it's going to be the x value here, which is the longer one, not the small one. Sine of 30 is half, so the cosine gets the root 3 over 2. There we go. Not too bad. How about this guy? Ooh, this looks complicated. Okay, if sine of some number t is a, cosine of t is b, and tangent of t is c, we want to find the tangent of t plus pi minus cosine of t plus 2 pi plus the sine of t plus 4 pi. Interesting. Okay, this is just symmetry at work here. So let's start with probably the toughest one, actually, is the tangent of t over pi. Remember, tangent is sine over cosine, which means it equals the y value over the x value. Okay, it's the ratio of the two. So let's check. Wherever t goes, I don't know where t is, but I do know how adding pi can affect whatever t was. Okay? So let's take a look at our circle. If t was here, let's use the simplest. Pretend t was 30 degrees, or pi over 6. If you add another pi to it, that's a half circle. So instead of up here, we're now over here. How does that compare? If I have my circle filled in, and we put our numbers in there, that would be negative root 3 over 2, comma, negative 1/2. These values are the same as this one, except they're all negative, right? We agree with that? And so the tangent is the ratio of one by the other, this divided by that. Well, now instead I'm taking this divided by that. It's the same numbers, except they're negative. Oh, but it's a double negative, right? A negative divided by a negative is still positive. I'm going to get the same thing. Does anybody doubt why we get the same thing? Tangent of t plus pi equals the tangent of t. Which means it equals c. Right? Look at the next one. Cosine of t plus 2 pi. 2 pi is a full circle. We've gone all the way around and met up at the exact same angle. It's t plus 2 pi is coterminal with t. It's the same angle. We just took the long way around, right? You drove around the block again and got nowhere. So this is still the cosine of c, of t, which means they told us that was b. So it's just b again. So far we have c minus b plus whatever this thing is. 4 pi is twice around the circle. Doesn't change a thing. You still land on the same spot. All right, you're flipping the twister spinner. Doesn't matter how many times it wraps its way around, it still lands in the same space. So this sine of t plus 4 pi is the same as sine of t, which is a. So this is c minus b plus a. That's it. Boy, that looked kind of terrible, didn't it? It was like, oh gosh, this might be complicated. Oh, it's not. It's not so bad. They're periodic functions. They repeat themselves. They're periodic functions. They repeat themselves. I don't have time for that. We got to keep going. All right, word problem. The height of the water h in feet at a boat dock is t hours after 6 a.m. is given by some equation. We'll read it later. Find the height of the water at the dock at 9 p.m. Okay. We have at some time, I want to find the height. We have a function for height, which is a function of time. So all I got to do is plug in the time into this function, and I will get the result out. Sounds pretty good, so let's try it. Okay, h equals 8 minus 3 sine pi over 6 times 9? No. Don't plug in 9. Okay, this is hours after 6 a.m. How many hours after 6 a.m. is 9 p.m.? 9 p.m. is only 9 hours after 12, right? And so it's another 6 hours from 6 to get to 12. Okay, clocks are confusing. So 9 plus 6, 15 hours. 15 hours later. So this is times 15. Aha. Okay, pi over 6 times 15. Quick reduction. That divided by 3 is 2. That divided by 3 is 5. We're at 5 pi over 2. Take a look at our unit circle. 5 pi's over 2. Pi over 2 is a quarter of a circle. Oh, I'm going to be on an axis. Easy mode, right? Relax. Like, oh, good. This is going to be one of the simple results. Because our answer literally is going to be 0 or 1 or negative 1. So let's count. 1, 2, 3, 4, 5 pi's over 2. We're at 0, 1. We're looking for the sign, ask for the y value, so it's 1. This is 8 minus 3 times 1. That would be 5. The answer is 5 feet. Did you think that was going to be scarier? I bet you did. Wasn't terrible, right? Okay, any questions on those examples so far? No? All right, let's keep going. Final point for the day. The identities. Okay, here's the thing that no algebra book makes clear, and unfortunately even our PreCalc book, as good as it is, doesn't really set you up for what the heck is the point of these stupid things. The identities are shortcuts to make ugly functions more manageable in calculus. That's their only purpose, right? Somebody sat down and said, you know what, doing this looks like a nightmare, especially when you go into calculus and you're like, okay, now find the integral of that from 0 to pi over 3. And you're like, right? Suddenly it gets wacky. And so, in my opinion, the trig identities were developed specifically to make calculus of trig functions easier. Okay? You've already encountered in the text some real-life application questions, and you'll see more in today's homework, where the trig functions are useful, right? They're very applicable to things around us. So we can't ignore them. And we understand at this point that calculus is very useful, very applicable for doing things in the real world. So we don't discount all of that. But it does create for some messy computations. And before they had computers, they could just do it all the hard way. Like, we need to find a way to make this thing look better so I can do it by hand. That's the whole purpose of the trig identities. And even before calculus, they could make some questions for us in PreCalc easier, even if they're just basic algebra and trig type questions. So, for example, here we have some angle theta is, we know it's an acute angle, and the cosine of theta is square root 31 over 9. Can you use the Pythagorean identity to find sine of theta? Now remember the way you used to do this. If you didn't have the Pythagorean identity, you would have to construct your right triangle. You say, okay, this is theta, cosine is adjacent over hypotenuse, so catoa, and so that means the hypotenuse is 9 and the adjacent side is square root 31, right? And you'd have to use the Pythagorean theorem to solve for this opposite side, and then you could set up the ratio of that over the 9 to get the sine of theta. It's fairly involved. There's a lot of steps there. Instead, the Pythagorean identity is a shortcut. Somebody has translated the Pythagorean theorem, right? A squared plus b squared equals c squared. On the unit circle, c is always 1. Our a and b, the sides of our triangle, are always x and y. X squared plus y squared equals 1, which is actually now the equation of the unit circle. It comes from the Pythagorean theorem. And we know we can always get our x value from the cosine. We can always get our y value from the sine. Cosine squared plus sine squared equals 1. That's the Pythagorean identity. It's the Pythagorean theorem, but written with trig functions, the trig ratios, right? And we have 3 wonderful versions of it. Not only can it be sine and cosine, check this out. If I take all of these and divide by sine, or specifically, sorry, sine squared, right? Sine squared over sine squared is 1. Cosine over sine, where have I seen that before? That defines something. Well, I know sine over cosine is tangent. I have the reverse of that, reciprocal, cosine over sine. Oh, that's reciprocal of tangent is cotangent. Okay, but I've got them squared, right? We did it twice. So I get cotangent squared. And 1 over sine is defined as a cosecant. Again, this is squared, so now it's cosecant squared. Look at this. 1 plus cotangent squared equals cosecant squared. That's how they got the other ones, okay? This is the same thing. We just divided everything by sine squared. This is the same thing, but we divided everything by cosine squared. They're all the same. Use whichever one you like. Okay? You don't need to remember all of these. If you can remember this guy, because it's just Pythagorean theorem, You can fancy it up and make a different version. And this is going to be real handy because it looks like I have cosine. I want to solve for sine. Okay, well, let's use our Pythagorean identity. Let's try that. So sine squared of theta plus cosine squared of theta equals 1. In this case, our cosine would be this, but we want cosine squared, so we'll square that. Square of square root 31 over 9 squared. All right? So use your exponent properties. All right? That means this gets squared. That's 31. 9 squared is 81. So for sine squared theta, we're going to subtract 31/81ths from 1. So let's turn this into 81 over 81. 81 minus 31 would give us 50. Over 81. And we only want one sine, not the sine squared. So we're going to square root the whole thing. All right, we can reduce that a little bit, right? Because we can at least do that. The denominator is a perfect square. It's fine. Anybody know square root of 50? It's really close. Almost 49 would be 7, so it's something slightly more than 7. 50 is 5 times 5 times 2, right? You can factor tree that down, so we can pull the 5 out and say that's 5 root 2 over 9. Is that my final answer? Yes, it was. There we go. I don't know if that's necessarily faster than whipping up your triangle and running the Pythagorean theorem itself, but it kind of groups everything all together. Our calculation is very similar because it's the same thing. Any questions there? No? How are we doing on time? My sense of class times was thrown off yesterday, 35. Okay, we still got time. Let's keep going. One more example. This ugly mug, right? Oh my gosh. CSC, COT, cosecant? No, nobody uses cosecant. I hate cosecant. Fine. All right, I'll use the cosecant. Use an identity. Let's find an identity. Cosecant. Okay, I'm just going to shortcut back to these because they're already written down. Right? Is there one that involves cosecant and cotangent? Yes, right? It's the same thing. We divided the good old Pythagorean identity by sine squared, and we got left with this. 1 plus cotangent squared equals cosecant squared. So let's write that down. 1 plus cotangent squared equals cosecant squared of, what did they use? X, t. Doesn't matter. Whatever variable you like. I'm a fan of theta. Doesn't matter. In this case, it's pi over 5. First thing I would do if presented with this is check, are the arguments of my trig functions the same? If these are not both pi over 5, then I'm in big trouble. Okay, it's going to be a lot more complicated. We got to use double angle formulas, half angle formulas, or something like that to get them to match. Okay, we can only do fun stuff if they match. Thankfully, they do. So, looks like I have cosecant squared minus cotangent squared. What happens if I subtract cotangent from both sides? I get 1 equals cosecant squared minus cotangent squared. With me there? It literally does not matter what is in there. The fact that's pi over 5, I don't care. As long as they are the same thing, it matches this form of the equation right there. The answer is 1. Wait, really? This whole mess is just 1? Are you serious? Oh. Well, that's handy. So the integral from 0 to pi over 3 of this is just the integral from 0 to pi over 3 of 1? Oh my gosh, you've got to be kidding me. Yeah, that's exactly it. So it's a flat rectangle. The answer is just pi over 3. There you go. Using the trig identities to make seemingly ugly things simpler. Now, full disclosure, right? You're still on the practice. We're still in PreCalc. So the actual questions presented to you using these identities seem like busy work. It seems like, okay, but it doesn't actually change anything. What's the point? Remember, you're practicing. Practice the skill of changing from one form to another so that later when you encounter it in the context of a bigger, messier problem, that part will not intimidate you. Oh, well, I can simplify this to make it look like that. And now the rest of the problem becomes much more manageable. Does that make sense? But don't scare you off. Okay. Last call for questions. No? Okay, that's all I've got for you here. Then we've still got a good 9 minutes left. Go ahead and get started on your exercises, your homework for today. And I'll leave you with a bit of time to work. I do recommend that you read through all of them first, get a feel for where they're all coming from. That way, while I'm here and we're live, you can ask me a quick question if you see something that scares you more than the rest. All right? Otherwise, I will sit back and let you work.